Section 12.1, sequences. So a sequence is a function whose domain is the set of negative integers. So let's take a sequence. So let's take the sequence f of n equals 1 over n. And all we're going to do here is make a list of these values or terms here. So let's take a look at the first one. So when I plug in a 1 here, we call that f of 1. So my list would be f of 1, comma, f of 2, comma, f of 3, dot, dot, dot. Or I could write it 1, comma, 1/2, comma, 1/3, comma, 1/4, comma, dot, dot, dot. So the thing is, when I'm talking about these sequences, they're really just a list of numbers. But the domain of these numbers is the set of non-negative integers. So now that's the idea here. So another way to represent this f of 1, f of 2 is a1, a2, a3, a4, comma, dot, dot, dot. So that's another way we actually see sequences being talked about, using this a sub 1, a sub 2, and it wouldn't be an fn, but over here it would be an a sub n equals 1 over n. And this is more of how they're referred to over here. Now, to formally talk about these sequences, if I was using my right notation here, this a sub n, I usually have it in a set of these braces. And a lot of times when you see these represented, you'll see them this way, and sometimes you'll see them with values here off to the right. So n equals 1 to infinity. So this is an infinite sequence here that we're actually talking about. So that's another way you could see it represented. Now this book doesn't do it that way, so I'll take those away for now, but I wanted to point that out to you. And if I was going to write it for the one we had, this would just be a brace, 1 over n brace. And that's what it would look like if I was going to talk about this sequence formally. So let's take a look at this problem. It says write down the first 5 terms of each equation. And here's the, not of each equation, of each sequence, excuse me. So anyway, so we just got to write down the first 5 terms. So we need a1, a2, a3, a4, and a5. That would be the first 5 terms. So this simply means here, if I'm going to get a 1, I'm going to plug in 1 for my n in both the top and the bottom here. So that means for this first term, it would be 2, 1, plus 1. And on the bottom, it would be 3, 1, minus 1. So this first term then would be 3 halves. And then I would just do that with the second as well. And I'll just do the first couple so you can kind of see how that works. So then this is going to be a 2 in there now. And then this is going to be a 2 down here as well. And that's going to be 4 plus 1, which is 5. And then on the bottom is going to be 6 minus 1, which is 5. So that actually is going to be 1. But I'm going to leave it this way. One thing I want you to see here, just for now, because I want you to see the pattern here. Now I'm going to do one more. Actually, I was going to stop there, but I'm going to do one more because I want you to see this. So this is going to be a 3 in there now, over 3 times 3 here, minus 1. So this is going to be a 6 here, plus 1 is 7. So that's going to be a 7 over 9 and 8 here. Okay, so now I'm going to show you what's really going on here. So when I look at this pattern, there's a separate pattern on top and bottom here that I'm seeing. So for instance, if I look at this jump here, that jump was 2. And if I look at that jump just on the top, that was a 2 more. Now that comes from this number here, the multiplier of my x. I kind of think of it like a slope. So that's really handy when I'm thinking of these sequences. Now look at the bottom here. That means for the bottom one, I should have a jump of 3. So again, when I started my first one, it was 2. And then when I go to the next one, that's 3 more. And then when I go to the next one, that's 3 more. So now without actually punching a lot of stuff in and plugging it in my handy dandy formula there, I could finish this pattern out. And this works anytime I see something that kind of looks like a line in a way. If I put a y on that, y equals, that would be a line. So in essence, that's the way I kind of think of these problems. So then for the next one, the top would be a difference of 2. So that's going to be a 9 here. And the bottom is a difference of 3, so that's going to be 11. And then the next one's going to be an 11 on the top, and then on the bottom is going to be a 14. So there's the first 5 terms. Now these types are easy to work with for that reason. So now let's take a look at the next one here. So here's another one. This one says, write down the first 5 terms of each sequence. Now this one we're going to do the same way, but we may not pick up on the pattern as easy, but we might, we'll see. Okay, so then I'm just going to do A1, A2, A3, A4, and A5. All right, so there we go. So now we're just going to plug in 1 because that's what that little 1 down there means. I'm going to plug in 1 for my ends. Okay, so that's really going to be 3 to the 1 over 1 factorial. Now, I don't know if you're familiar with factorials or not, but the way factorials work are, so for instance, let's say I had 6 factorial. This means this would be 6 times 5 times 4 times 3 times 2 times 1. So in essence, what I do for a factorial is the number I see is the number I start with, and I just count down to 1 and times them all. That's how the factorials work. So for instance, if I had like a 23 factorial. Now I'm not going to write all these out. It's going to be 23 times 22 times dot 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 times 3 times 2 times 1. And you know what's in between this dot 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 here, right? Okay, that's 21, 20, 19, 18, all the way down. So that's the idea of these factorials. And there's a few more ideas to take from this idea of factorial. 1 factorial is 1 because it's just a 1 I have. And then 0 factorial is the other one that catches people up. 0 factorial is actually 1. Something to make a mental note of. So if you ever see a 0 factorial, you know it's 1. All right, so back to our problem. Okay, so 3 to the first is 3, and 1 factorial is 1. So I'm just going to write this down here as 3 over 1 for now. So you know where everything's coming from. And then that's actually just going to be 3 when I simplify it. And I should, but again, I just wanted to leave it there for now. Okay, so now the second one, A2. So that means that's going to be 3 squared over 2 factorial. And 2 factorial is just 2 times 1. So this is, 2 times 1. So that's going to be 2. So it's going to be 9/2 for that one. Now the next one's going to be a 3 here. So that's 3 to the third over 3 factorial. So 3 to the third is 27. And 3 factorial is 3 times 2 times 1, which is actually 6. And that reduces 2. So just kind of keep that in mind for these. But I just want to keep going with this. So 3 to the 4th over 4 factorial. So 3 to the 4th is 81. And 4 factorial is 4 times 3 times 2 times 1, but 3 times 2 times 1 was 6, remember that? So all I have to do is multiply that by 4, and I'll have the next number. So that would be 24. And the last one we need to find is 3 to the 5th. Over 5 factorial. And that would be 243 over, and again, 4 factorial was 24. So 5 factorial would be that 24 times 5. So that would be 120. So there's our 5 terms for this sequence. Now again, I can simplify them, and I will, just for the sake of a final correct answer. And 3 goes into both of those. That's going to be a 9 over 2. Is that right? Wow. And 81 over, and then 81 over 24. Those both have a 3 in them. So that's going to be 27 over 8. And then the last one is 243. 81 over 40. So this would be the answer for this problem here. Okay. So now you kind of get an idea of how these sequences work. We learned about factorials. So there we go.